Hi everyone. So we've been able to look at source-free RC and RL circuits and also solve some problems and also explain the time constant. Now we're going over to step response circuits. So remember how for source-free, the whole idea is that we're looking at the effects of the circuit by the sudden ejection of a source. So let's say we're dealing with RC, with a source-free RC. For instance, we had a capacitor, we had a resistor over and ground, and we're looking at, okay, this capacitor has been charging up for a while. At t greater than zero, we suddenly remove the power source that has been governing this capacitor, and it's going to decay this way. So that's what we're dealing with. That's what we dealt with when we're talking about source-free circuits. For step response, however, and write that down. For step response circuits, it's quite the opposite. So for source-free circuits, you didn't have any sources here, because you see over here there are no sources whatsoever. But for step response, you're looking at the response of a circuit by the sudden application of a power source. So it could be either voltage or current. So now let's still deal with RC. So now let's say we wanted to model a step response RC circuit. At t greater than 0, we're still going to have a source. So let's make this our resistor and make this our capacitor. So that's essentially the difference between source-free and step response. And now our graph isn't going to look the same way as it did with the source-free. Because remember, with source-free, there are no... Okay, let's go to this voltage, make this time. This is 0. So over time, the voltage for this source-free RC circuit is going to tend to 0. Because apart from this decaying capacitor, right, there's no other thing here that can supply power. But for step response, look out, we have a source here. So this is definitely going to still have an effect in the circuit. So that the graph is going to look something different. We'll explain this in more detail. So let's just say this is V0. This is the voltage of the source. So it's to look something like this over time. Okay, so that's just to get the theory done before we start deriving. So how do we derive the step response RC circuits? We're already familiar with resistors, we're already familiar with capacitors, so let's go straight into it. What will usually happen, okay, let's model our resistance R, give ourselves a switch. Ooh, I don't like this. Okay, give ourselves a switch, then our capacitor. And then over here, we're going to have our voltage source. Alright, so we'll call this Vs as voltage at the source. This is going to be R for our resistor, and this is going to be C for our capacitor. So what happens for step response circuits? Our capacitor is going to be charged to an initial voltage V0. Initial voltage V0, okay? This is going to help us in our calculations. So this capacitor is going to have an initial voltage. In the questions we may have, we may be given this initially. We may have to solve for it at t less than 0, and at t greater than 0, we'll have a different circuit. Vs is the voltage across the source. This Vs over here, right? So at t greater than 0, we're going to have a source in our circuits. That's how you know it's step response. For source-free, there are no sources. For step response, there's definitely going to be a source. So at t greater than 0, we're going to have the source Vs, a certain voltage, and this is also going to play an important role, and usually a resistor of resistance R. So what happens is that you have an initial capacitor voltage V0, and at t equals 0, the switch is going to close. Okay, so once the switch closes at t equals 0, let me write that down. At t equals 0, your circuit gets completed. All right, and then you just have your nice RC loop, simple and straightforward. But what we do to try to avoid having to draw switches and directions and everything over time, is that we say our voltage source, our source in the circuit, has a certain voltage, Vs. That's the same thing we had before, but this time it's going to be Vs multiplied by U of t. Multiplied by U of t. All right, this is a little foreign. I'm going to explain what this is. U of t is what we call the unit step function. The unit step function. And what it does is actually very simple. It helps us no longer have to use switches to make a source appear at a certain time or disappear at a certain time. What do I mean? It's a tool, right? And it's going to have values at different times. So U of t at t less than 0 is going to be 0. Okay? But t greater than 0 or equal to 0 is going to have a value of 1. All right, so let's say we have a graph. Okay, let's say we're looking at a certain voltage. All right, let's say we have a voltage source. Let's say we have a voltage source somewhere here, plus or minus 20 volts. All right, and we made this 20 volts U of t, or 20 U of t volts. Okay, what does this mean? Our time is going to be on this axis. Okay, so this is time, this is voltage. All right, so this is t less than 0. This entire region is t less than 0. This entire region is t greater than 0. So as long as this function is 20 U of t volts, that means that for t less than 0, the 20 volts is going to be multiplied by 0. So there's going to be no voltage across this as long as the time is less than 0. Okay? But once we get to t equals 0, okay, that's here. Once we get to t equals 0, our voltage comes alive, now has a value of 1. So the value of this voltage is now going to be 20 times 1, which is 20 volts. So you see, it doesn't have that much, and it doesn't have an effect on the calculations. It's a pointer, it's a symbol, it's a tool to help us know, all right, when is this coming on, when is this coming off? So if we were to draw this, this was 0 all through. At t equals 0, it's going to come up to the 20 volts and maintain that same voltage throughout. All right, I hope that was clear. All right. Okay. Ooh. So that's what happens when we're dealing with the unit step function. That's why we bring it in, usually so we don't have to, keep using and reusing switches. So let's get to the derivation of the step response RC circuits. So this is our resistor R. It's going to have a voltage this way. Voltage across the resistor. This is our capacitor. All right, this is our voltage source. We can make this a ground circuit. All right, and then we're going to make an analysis over this node here. So by definition, we're going to have a current IR going this way, current to the resistor RR, current to the capacitor RC. Okay, so this is simple nodal analysis. All right, okay, and the voltage at this node, let's call it V. Okay, the voltage at this node is going to be V. All right, so this is simple nodal analysis, or KCL, Kirchhoff's current law. We have a node here, and we defined, all right, IR and RC are leaving the circuit. So what does that mean for mathematics? That means that IR plus RC are both going to equal 0, since they're both leaving the node. Agreed? All right. To find IR, recall, this is where nodal analysis comes in. The voltage at this node is going to be this. Remember, this is ground, so this is 0. The voltage here is 0. Okay, the voltage here is Vs. The Vs, that's the voltage at the source, U of t. Okay, so to find the voltage here, it's this minus this, and this is 0. So we're staying that way. So IR is going to be, voltage drops across the resistor. So we're going to do the voltage, meeting it, then subtract the voltage at the other end. So that's going to be V minus Vs U of t. So V minus Vs U of t all over R. Okay, remember we're looking for current. So current is voltage or resistance. And the current through our capacitor, usually very simple. That one doesn't change. C divided by T. Both of these equals 0. Amazing. We're going to, isolate dV dt to try and make our time constants come out somehow. So I'll start with dV dt. dV dt, dV divided by dt is equal to V over RC. Alright, so recall we're solving for the voltage at t greater than 0. So that means that this is going to equal 1. Remember the definition of our unit step function, okay, is 0 for t less than 0 and 1 for t greater than or equal to 0. So this is going to equal 1, and then we can straight up just write Vs over RC, okay, minus Vs over RC equals 0. Alright, let's take this to the other side. So we're going to end up with both of these to the other side, actually. So dV dt is equal to Vs, voltage at the source, over RC minus V over RC. So we can factorize that out. So that's Vs minus V, let's keep this in the brackets, all over RC, which is amazing work. But we're going to have to end up, because at the end of the day, we're trying to bring voltage back here, but we need a negative sign with RC so that we can have, the regular decaying exponential. So we're going to divide this by minus. We're going to factorize that minus 1 too. So that's going to be minus times V minus Vs all over RC. I hope you understand what I just did. If you multiply this 2 by, it's actually minus 1. Okay, negative 1. So if we multiply this 2 by minus 1, you're going to get minus V plus Vs, which is the same thing we have here. We just factored out minus 1. So all's fair, all still good. Okay, to bring the like terms together now, V minus Vs is going to come to be, dt is going to go to the other side. So we're going to have dV 1 over V minus Vs dV is equal to minus 1 over RC dt. Alright, this is looking familiar. The familiar integral we always end up with. So let's take the integral, okay, of these to simplify it so we can solve our differential equation. This is going to go from 0 to t. Okay, remember we're solving for t greater than, the expression for t greater than 0. Alright, so our lower limit is going to be 0. Our upper limit is going to be at what time? Okay, we're making a function, so we want this to be able to solve for the voltage at a time. That's why t is our upper function here. The lower function of this voltage side is going to be V naught. Okay, remember we're starting at t equals 0, so the lower bound is going to be, what's the voltage at t equals 0? So that's V naught, and the upper bound is going to be V of t. Okay, remember integrating 1 over a dA is going to be ln A, so that's ln V minus Vs, draw our bounds for V naught and V of t. That's going to equal minus 1 over RC times T. So minus T over RC. That bounds to 0 and T. Okay, let's move to another page. Alright, so remember what we had. Alright, so now we're just going to substitute the bounds to get rid of these limits. So how this works is that you have a variable here, that's V, minus 2 over RC, sorry. Oof. Okay. So you have a variable here, that's V. We have limits here, V of T and V naught. Is that clear? Okay. V of T and V naught. We have a variable here, T, and we have a limit T and 0. So how this works is that we sub the upper bound in, then subtract from what happens when you sub in the lower bounds. So let's go. That's V ln V of T minus Vs as voltage at the source. Then minus, then sub in the lower bound, ln V naught minus Vs. Okay, and that's going to equal to minus T over RC. Then minus, then sub in 0 here is 0 over RC. So this will tend to 0. We can erase the whole lot. Alright, so what's going to help us now is, logarithm tricks. Since we're subtracting logarithms, we can bring them into one and make it a fraction. So that's natural log of V of T minus the voltage at the source. All over V naught as the initial capacitor voltage minus the voltage at the source is going to equal to minus T over RC. Remember, we don't have any integration constants here because we did definite integrals. We had limit here, so there isn't going to be an integration constant. To get rid of these, we make both sides exponents of E, Euler's number, so that's going to cancel out ln. So that's V of T, voltage as a function of time, minus the voltage at the source, all over V naught minus the voltage at the source again is going to equal to E to the minus T over RC. So I'm going to make the substitution for time constant here, tau. Remember what we said in the last video, we covered it before. The time constant tau for an RC, both source free and step response, is going to be the resistance times the capacitance. Okay, it's important not to forget that. So we're going to solve that in for the time constant. So V of T minus the voltage at the source is going to equal V naught minus Vs e to the minus T over tau. That's a funny way to draw it. Alright, so we're through now. Just to arrange our terms together. Let's take out the fraction. Let's cross multiply, so we end up with only the numerator. So we have V as a function of time, which is what we're looking for, minus the voltage at the source is equal to, keep this in bracket, V naught minus Vs e to the minus T over time constant. Alright, so now what we have to do, just take the voltage at the source to the other side, and you're going to have the voltage of the capacitor as a function of time is equal to Vs plus V naught minus Vs e to the minus T over the time constant, which is a very elegant formula. So what does this mean? Let me redraw the circuit. We have a voltage source here, we have a resistor, we have a capacitor. Okay? And this is, let's say, 5 volts U as a function of time. What does that mean? This is C, this is R. What does that mean? At t less than 0, okay, keep in mind the unit function is the backbone of all of this. Is 0 for t less than 0 and 1 for t greater than or equal to 0. U of E of t. Okay. So what does this mean? It means that, we're looking at the circuit over a particular time. Okay, so t less than 0. At t less than 0, okay, the unit function is 0. So that means this voltage is 0. There's 0 volts over here, 0 volts over here, which could be you can see it as a short circuit. But essentially, that means our circuit is not yet active. All right. Once our time reaches 0 here, this comes into play and becomes plainly 5 volts. That's the voltage at the source. And then we can now watch for our response of the circuits. So if we were to look at this, graphically, you end up with something that looks like, plotting the behavior over time. Okay, let's call this, let's call this V0. And let's call this Vs. Okay, t equals 0, voltage. So what is going to happen is that this graph is going to look something like this. It's going to start with the initial voltage of the capacitor and then increase sort of exponential manner and then even out at the voltage at the source. All right, that is why, if you take the limits of this to infinity, Vs, the voltage is going to be equal to Vs. That's why in some cases you can see Vs being replaced by V infinity. So another way you can see the formula would be, V of t is equal to V infinity plus V0 minus V infinity e to the minus t over time constant. These are both absolutely correct ways of expressing the circuits because it sees the same thing. And another thing I want to point out is, let's say, for instance, that we don't have a source. We don't have a source here. Okay, the value of this source, the voltage at infinity, V infinity is equal to 0 or Vs is equal to 0. Let's look at our formula and see what happens. If Vs is equal to 0, this goes. Okay, so nothing is being added. And this goes, so nothing is being subtracted. So we sort of end up with V of t is equal to V0 e to the minus t over tau, which is the formula for a source-free RC circuit. So you kind of see how the step response can simplify to the source-free when there's no, external voltage involved. So I hope that I was able to explain that.